So we mentioned in a previous video that amino acids have left-handed and right-handed forms, just like you have a left hand and right hand as well. Well, we also saw the same thing that happened in carbohydrates. We looked at carbohydrates and we said that most of these are D carbohydrates. They were right-handed as far as the rotation goes around the chiral center. And now we know that almost all of the amino acids that we are going to see, with the exception of one, and that was our simplest amino acid of glycine, but all of these other amino acids are chiral, which means that they all have a left hand and right hand form. And we also said that Mother Nature played a trick this time around because she picked right-handed sugars, but she picked left-handed amino acids. So left-handed amino acids are really the most common amino acids that are out there, and that is what we call the biologically active amino acids. So back in the day with carbohydrates, we talked about a Fischer projection, and we started with the carbonyl up here at the top, and then maybe down here at the bottom was a CH2OH, and we'll keep it simple. We'll just put one carbon in between, and we'll put an OH here and an H there. And we said that with these Fischer projections, we have to understand that the head and the tail point away from us, and the things on the backbone point toward you. So I'm going to just write that over here to the side. So the head and the tail, they point away, and the atoms on the backbone point toward you. Okay, so this gave us maybe some insight onto some of the 3D shape that these structures begin to take on. And again, if you've not done it yet, I would highly encourage you to maybe take a model kit, take a look at the structure of a carbohydrate, make it this way, and prove to yourself that you can in fact have the things on the backbone point toward you and the head and the tail point away from you. So just do it, make sure that you fully understand it. And we said that we focus on the OH group. And we said if the OH group is on the right-hand side, then we call this the D sugar. And if that OH group is on the left-hand side, we call that the L sugar. And we really only focus on the last chiral carbon of the sugar. So that was a review of carbohydrate Fischer projection. But guess what? The amino acid Fischer projection is very, very similar. So we saw that we do have a COOH, right? So that COOH group has lost a proton because we're talking about physiological pH here. So we see a C double bond OO at the top, very similar to the actual sugar itself. Our carbonyl is up at the top here, our carbonyl is up at the top there. The only difference is that we have to understand that this is an aldehyde that's drawn on the sugar side, but this is a carboxylic acid that's drawn on the sugar side, right? That was a COOH. We've removed a proton, however. Okay, so down here at the bottom, typically in the Fischer projection, we put the R group. And that R group is the group that changed, that made different amino acids for us. So this is the hydrogen, or this is the CH3 group, or this is the isopropyl group. This is the isobutyl group, the sec-butyl group, the big, huge structure for tryptophan. That's the R group that randomly changed, that made these different amino acids for you. So that's typically drawn at the bottom, the tail of the amino acid. And then on the backbone of the amino acid, we typically have a NH3 that's carrying a positive charge. Again, we got to keep physiological pH in mind. And then we see the hydrogen that's over to the left. Okay, so this is the kind of the template for the Fischer projection that you should be drawing and training yourself to analyze and look at. Well, the difference here, we already said COOH up at the top, but another difference is the NH3 group. And on the sugars, it was an OH group. And on the amino acids is, of course, the amino group, the NH3 group, that's the positive one. This Fischer projection, if it's drawn this way, it's the same structure. The things up at the top and the bottom, they point away. There's no difference when that Fischer projection is drawn with a carbohydrate or an amino acid. And the groups on the backbone point toward you, just like before. There's no difference there either. And to make matters even easier, this NH3 group, well, this gives you the direction of the amino acid. And if it's on the right-hand side, this is the D form of the amino acid. So this amino acid Fischer projection, well, that's not really what we would see normally in our body. We would see the L form in our body, right? So what I would typically draw for the amino acid structure is something that looks like this. And this is the L form of the amino acid, and that is our left-hand form that we will need. So there's the story with the Fischer projection. It really isn't any different than the carbohydrates are concerned. If you can do the carbohydrate structure for Fischer, you can do the amino acid structure for Fischer. There is something else that I want to look at when it concerns the structure of the amino acids, however. We have a chiral carbon, and we know that chiral carbons give us this 3D geometry where we've got this solid and this dashed wedge. And let's just take the structure for alanine. So NH3, carbon, hydrogen, COO minus, and then for alanine we have a CH3 group that's down here on the R. And I want to convert that over to a perspective formula. This formula that shows me the dashed wedge and the solid wedge. So how do I convert that over and show the L form? Okay, that's what we're after. So how do I do the L form? Well, if I'm given a choice on how to draw it, you do it just like you've always done it. This hydrogen is the lowest priority group, and hopefully that hydrogen will be on the back end of the molecule. It points away from you and your point of perspective, which is why it's called perspective formula. Okay, well, what's my highest priority group here? Again, you go by the atomic number. So what we have attached to this chiral carbon, this is the chiral carbon right there. Okay, we've got a nitrogen, a carbon, and a carbon. The nitrogen has a higher atomic number than the carbon does. So that means the nitrogen gets highest priority, and I would probably prefer to draw that up at the top. Now, if I'm given a choice, that's where I would want it. Maybe they're going to be drawn for me, and I have to determine is this D or L, and things can get a little trickier. But if I'm given the opportunity to structure it the way that I want to structure it, then that's typically what I would do. Lowest priority, which is typically hydrogen on the dashed wedge, and then we see our NH3 group up at the top because that's going to be our highest priority almost every single time. And then I see the CO, C, and C. These two are tied, so I go to the next atom. The next atom is oxygen here, and the next atom is hydrogen there. So that means the COO minus comes in second. Well, I want to make sure that I do the L form. So this needs to turn left-handed for me. I need this kind of rotation. So that means what's next in line should be my COO minus group. And then what's next in line is finally my R group, which is, in this case, a CH3. So this is the perspective formula of L-alanine. So all of that general kind of organic stereochemistry back in the summer, all of that's coming back again 2 semesters later on how to draw a perspective formula and how to rank these priority groups. So that's something that never went away, and you're seeing that creep back up. So again, if you're kind of rusty on that stereochemistry, I would encourage you to go to that playlist in YouTube and watch the stereochemistry folder and take a look at what R and S and how to determine these groups. We spent close to 40 videos discussing how to draw these types of structures. So that's how you rank them. There's no difference in the ranking. Amino typically is always highest priority. Your carboxylate, your COO group typically always is the second priority, and then your R group is typically your third priority. So just double check them, double check the priorities, double check the rankings, but that's typically how they fall in order. So what I will do here is that I will do a 1 and a 2 and a 3. So amino's typically ranked 1, your COO is typically ranked 2, and then finally your R group, because this typically always started with a CH2 at least. Very rarely did we have something else other than carbon that was on that position, but that was ranked as number 3. Okay, so there's the story with D and L, and I would maybe tell you to take a look at your chapter as well. Make sure that you can answer some of those stereochemistry questions. I won't do any examples here because this just kind of reviews some of those questions, but take a look at some of these questions. Make sure that you can identify a D or an L amino acid. You're going to see that in your homework, you'll see that in the quizzes, and you'll see that on the test. So just make sure that you feel comfortable with it and you'll be okay. So in the next video, what we will begin to look at is something called an isoelectric point, which is very important concerning identification purposes. So stay tuned. 10 minutes from now, we will finish isoelectric. You're going to see that it's a calculation, but it's not a very hard one. And you're also going to see how it will relate to various other techniques that we can bring into the picture on identification and analysis of these amino acids that we're working with.